Imagine instantly transporting yourself from New York to Tokyo in the blink of an eye. Fascinating, isn't it? This is the concept of teleportation, a staple of science fiction, but could it actually exist in our reality? Let's dive into the world of quantum physics to find out. Teleportation has long been a concept of fascination and speculation. From the teleporter in Star Trek to the Flu network in Harry Potter, the idea of bypassing the constraints of time and space to instantly travel from one place to another has been a captivating element of science fiction. But what if I told you that this concept isn't entirely fictional? Welcome to the world of quantum physics, a realm where particles can exist in multiple states at once, where they can be entangled in such a way that the state of one instantly affects the state of the other, regardless of the distance between them. It's a world that challenges our everyday perception of reality, and it just might hold the key to making teleportation a reality. But before we get too excited, let's clarify something important. Quantum teleportation, as scientists understand it today, isn't about teleporting matter like humans or apples from one place to another. Instead, it's about teleporting information about the state of a quantum particle. Here's how it works. Quantum teleportation relies on a phenomenon known as entanglement, where two particles are intrinsically linked and the state of one instantly influences the state of the other. Using this entanglement, information about the state of a particle can be instantly transferred or teleported to another particle, no matter how far apart they are. So, while we might not be able to teleport ourselves to a beach in Hawaii anytime soon, the implications of quantum teleportation are still profound. It could revolutionize the way we transmit and secure information, paving the way for ultra-fast, ultra-secure communication networks. So let's embark on this intriguing journey into the realm of quantum teleportation. Buckle up as we delve deeper into the quantum world. To understand teleportation in the quantum world, we first need to grasp a key principle: quantum entanglement. Now let's dive into this fascinating phenomenon. Quantum entanglement, in the simplest terms, is a bond between two particles, so strong that no matter how far apart they are, whether it's across the room or across the universe, the state of one particle will instantly affect the state of the other. Imagine you have a pair of magical dice. You roll them, and no matter where they land, they always show the same number. This is similar to how entangled particles behave. If you measure the spin of one particle, you instantly know the spin of the other, no matter the distance. This puzzling property of quantum particles was famously described by Albert Einstein as spooky action at a distance. And it's indeed spooky because it seems to defy the limits of space and time as we understand them. Now you might be wondering, how do particles get entangled in the first place? Well, it usually happens when particles are created at the same time and place or through certain interactions. Once they are entangled, they become a single system. Changing the state of one particle changes the state of the entire system instantaneously. But let's be clear, this isn't some sort of telepathic communication. It's not that one particle is sending a signal to the other. It's that the two particles, no matter how far apart, are still intimately connected. They are, in a sense, one and the same. Quantum entanglement, strange as it sounds, is the first step towards understanding teleportation. But there's more to it. Let's move on to another critical principle: quantum superposition. Now, let's introduce another crucial player in our teleportation story: quantum superposition. This principle is like the ultimate game changer in the quantum world. It's the idea that a quantum particle can exist in multiple states at once, and only when we observe or measure it does it choose a definite state. Imagine you're in a room with a box. Inside that box there's a cat. According to quantum superposition, until you open the box, the cat is both alive and dead. The act of opening the box of observation forces the universe to collapse the superposition and make a choice. The cat is either alive or dead. But it's not just cats in boxes. This principle applies to all quantum particles. Take an electron, for instance. It can spin in two directions at once, up and down. But the moment we measure it, the electron decides whether it's spinning up or down. It's as if the act of observing forces the universe to make a choice. This is a mind-bending concept, to say the least. It defies our everyday experiences and our understanding of reality. But it's one of the core principles of quantum mechanics, tested and confirmed in countless experiments. Now you might be wondering, what does superposition have to do with teleportation? Well, it's the combination of superposition and entanglement that makes teleportation theoretically possible. Here's how it works. If we have a pair of entangled particles, they're in a superposition of states. When we measure one particle, it chooses a state, and its entangled partner instantly chooses the corresponding state, no matter how far apart they are. This instantaneous, spooky action is what could potentially allow us to teleport information from one place to another. Combining quantum entanglement and superposition, we're now ready to dive into the heart of quantum teleportation. It's a journey into a world where the impossible becomes possible, where reality is stranger than fiction. So, strap in and prepare for a wild ride into the quantum realm. Scientists have already made remarkable strides in quantum teleportation. Let's take a look at some of these groundbreaking experiments. In the late 90s, a team of physicists at the University of Innsbruck in Austria successfully teleported photons across a laboratory table. This feat, while seemingly minor, was a monumental step in proving that quantum teleportation was more than just a theoretical concept. Fast forward to 2013, and the same team managed to teleport information between two particles located 144 kilometers apart. This experiment, conducted across the Canary Islands, showcased the power of entanglement and its potential for long-distance quantum communication. More recently, in 2017, Chinese scientists took a leap forward by teleporting a photon to a satellite orbiting over 500 kilometers above the Earth. This feat demonstrated the possibility of quantum teleportation in space, opening up new avenues for quantum communication networks. But it's not just about photons. In 2019, a team from the University of Science and Technology of China achieved the teleportation of a single electron state to a distant atom. This marks the first time that quantum teleportation has been achieved between two different types of particles. However, these experiments are not without their limitations. The process is incredibly delicate and requires precise control over the entangled particles. Additionally, the teleportation of complex objects such as atoms or molecules is currently beyond our technological capabilities. And when it comes to teleporting larger objects or living beings, well, we're still far from that reality. While we're still far from teleporting humans, these experiments are significant steps forward. But how would quantum teleportation theoretically work? Now let's break down the theoretical process of quantum teleportation. It all begins with quantum entanglement, a fascinating phenomenon where particles become intertwined in such a way that the state of one instantly influences the state of the other, no matter how far apart they might be. For teleportation, we need a pair of entangled particles. Let's call them particle A and particle B. Next, we introduce the particle we want to teleport. Let's call this particle C. Particle C is prepared in a particular quantum state that we want to teleport. This could represent a piece of information like a quantum bit or qubit in a quantum computer. Now comes the tricky part, the measurement. We perform a special kind of quantum measurement on both particle C and particle A. This measurement has an interesting effect. It destroys the quantum state of particle C and particle A, but at the same time, it teleports the state of particle C onto particle B. You might be thinking, wait a minute, how does particle B know what state to take on? That's where the magic of entanglement comes in. Because particle A and particle B are entangled, the measurement we performed on particle A and particle C instantaneously affects particle B, even if it's light years away. But there's one final step. To retrieve the original quantum state of particle C from particle B, we need to perform a specific operation on particle B. This operation depends on the outcome of our earlier measurement on particle A and particle C. Once this operation is performed, voila, the state of particle C has been teleported to particle B. So that's the basic process of quantum teleportation. But what could we use this technology for in the real world? Quantum teleportation is not just a fascinating concept, it has real-world applications, especially in the field of quantum communication. Quantum teleportation, as we've learned, involves the transfer of information between entangled particles, regardless of distance. Now imagine if we could apply this principle to communication networks. Think of it as the next step in the evolution of communication. We went from smoke signals to letters, then to telegraphs, telephones, and now the internet. Each transition has brought about faster and more efficient ways of transmitting information. Quantum teleportation could be the next leap forward. In a quantum communication network, information could be transmitted instantaneously and with perfect security. This is due to the unique properties of quantum entanglement. The moment you try to intercept or measure the entangled particles, the state of the particles changes. This alerts the network of a potential eavesdropper. It's like having a communication channel with built-in security that's practically unbreakable. But it's not just about secure communication. The principles of quantum teleportation could also be applied to other fields. For instance, in computing, quantum teleportation could be used to create super-fast and efficient quantum computers. These machines could solve complex problems in seconds that would take a classic computer millions of years. Healthcare could also benefit from this technology. Imagine a future where doctors could teleport medicine directly to the cells that need it. This could revolutionize the way we treat diseases and potentially save countless lives. Quantum teleportation has the potential to revolutionize communication. But as with any technology, it also comes with its set of challenges. It's not about beaming people or objects from one place to another, at least not yet. It's about transmitting information in a way that's faster and more secure than anything we've ever seen. And that in itself is pretty amazing. While the concept of quantum teleportation is thrilling, it's important to understand its limitations and the challenges we face. Quantum teleportation is a field where science fiction meets reality, but the path to this reality is not without its obstacles. One major stumbling block in quantum teleportation is the need for quantum entanglement. This phenomenon, where two particles become intrinsically linked and share properties instantaneously, is difficult to achieve. It requires precise conditions and immense control over the particles involved. The current state of technology can only maintain this entanglement for a limited time and over limited distances, posing a significant challenge to the practical application of quantum teleportation. Next, let's talk about technical constraints. The process of quantum teleportation involves complex operations at a quantum level that our present technology struggles to handle. For instance, scientists must be able to accurately measure the state of particles without disturbing them, a task which is far from simple in the quantum world. Moreover, there's the issue of fidelity, that is, ensuring the accuracy and reliability of the teleported quantum state. A high fidelity is crucial for the successful transmission of quantum information. However, maintaining this fidelity is a mammoth task due to the fragile nature of quantum states. Any interaction with the environment can lead to the loss of quantum information, a phenomenon known as quantum decoherence. On top of these, there are also conceptual challenges. Quantum teleportation doesn't transport matter, but rather information about the state of a quantum system. This is a radical departure from the traditional understanding of teleportation, and it raises questions about the nature of information and identity. Despite these challenges, scientists are continually striving to overcome these hurdles and push the boundaries of what we know about quantum teleportation. Quantum teleportation, once a concept confined to the realm of science fiction, is now a real field of study in quantum physics. We've journeyed together through the entangled world of quantum mechanics, exploring the principles of entanglement and superposition. We've delved into the groundbreaking experiments that are pushing the boundaries of what we once thought was possible. We've also faced the challenges and limitations head-on, understanding that this is a journey of discovery with many hurdles still to overcome. The potential applications of quantum teleportation are vast. Imagine a world where data transmission is instant and uncrackable, where exploration is not limited by physical distance, where transportation may take on a whole new meaning. This is the power of quantum teleportation. But with great power comes great responsibility, and it's up to us to navigate the ethical implications and societal impacts of such a technology. The realm of quantum physics is fascinating and mysterious, and who knows, maybe one day teleportation won't just be a concept in a sci-fi movie. What are your thoughts on this? Share in the comments below, and don't forget to like, subscribe, and share for more intriguing science discussions.